All right, so welcome everyone to the technical update session. My name is Michael Shoemate. I already introduced myself, so we'll skip through that. Uh, Today we're going to drop into the, the changes that have happened in the library in the last year. There's been a lot that's developed and a lot of really cool algorithms that have been added. So um, excited to share them with you. Um, so today we are um, kind of demonstrating a show at the Open Drive-In Theater. I'm taking some jokes and slides from last year. We have some new features. We have some key improvements, and we'll ultimately show some coming attractions. So we're building an OpenDP software ecosystem. I'm talking about the library today in particular. There's much more beyond just the library, as we've been talking about today. Deep Creator is another application that is built on top of the library and makes it possible for you to set up a server and a website where people can submit queries about a data set. Beyond just that, there's many more pieces that are in this OpenDP Commons. This is a bigger umbrella for projects that are under community governance that are related to the OpenDP project. There's quite a few things in here that aren't just code. There are some documentation, notebooks, test suites. We want to incorporate these kinds of things in the ecosystem. So beyond that, we have another layer of for example, Smart Noise SDK, which is a library developed and maintained by Microsoft for differentially private SQL and differentially private synthetic data. And these kind of systems use the OpenDP library and tools in the OpenDP Commons to make their feature set available. So we look forward to extending this with more libraries and tools that have been developed out there. If you have a need for a mechanism, then please use it and let me know, because we'd love to expand this. So this session's focus is on the library itself, and the kinds of things that underpin all these other pieces. So the library architecture is built all on from a core Rust implementation. On top of that, we have many algorithms that call upon the core implementation of the programming framework. And on top of that, you can build Rust applications. And since we support multiple languages, there's also a layer in Rust that lets us communicate with other languages. So as you're definitely familiar by this point, we have Python language bindings that call down into the Rust core. And other applications can be built on that, of course. We'll talk more about other bindings as we move forward. So I've shown the previous number of noise mechanisms or the previous number of data transformations on the left as of last year. And as of this year, that's gone up to 10 for the number of noise mechanisms we have. We have a lot more data transformations, and we haven't added any more combinators. I think the numbers here are a little shaky. It's not including mechanisms that are built out of other lower level mechanisms. But you could argue that those are mechanisms in and of themselves, and we have more than 10. I want to say that this is possible to the contributions from many people. I want to highlight some of the contributions from um, uh, um, Tudor and Shlomi, Abigail, many of you here in the audience. The feature set and things we make available are really built on these kinds of contributions we get from people. So I would say we could start with upcoming attractions. Well, the upcoming attractions from last year are now our feature attractions this year. So I'm pretty hyped to say that everything we promised last year in these slides are things that we support now. First off, Python's great to use, but what about some other language? I don't use Python per se. I use Rust, or I use R. So we now support working with OpenDP library from R. Drop those in there, and you can build other applications on top of that. The level of APIs of the R bindings is what we call the framework API, and that's what you're probably familiar with if you've worked with OpenDP software before. It's this shift chaining in order to build up computations, in order to build up what we call transformations or measurements from smaller transformations and measurements. So in this example, I'm showing, we're saying that starting from knowledge that we know that the data exists in this vector domain. The data is some kind of vector of integers, and we know that data sets differ in terms of additions and removals. Then we can build compositors, and we can build measurements that are tuned to that kind of metric space. It's become abundantly clear that this low-level API is not what most people want to use. They want to use something that's a bit higher level, and I'll get into that in a minute. But this is the foundation in which we build all of our software, and we kind of dress it up with APIs and higher levels. So the R language bindings are automatically generated from the same kinds of information that's available from Rust that we use to generate Python bindings. And so whenever you add another method to the Rust core, it's automatically available from Python and R, which helps reduce the maintenance overhead. Follows idiomatic R conventions. You might have noticed the pipes. It's nice that this time there's a language that's a bit more functionally oriented for our very functional framework API. It's available in our universe. You can install that package now and make DP releases with it. All right, so as I was mentioning before, these OpenDP APIs can be a little wonky. Like what's with all this functional programming stuff? So in response to community feedback about the difficulty of using these low-level APIs, we've released a new higher-level API we call the context API. The purpose of this is to simplify usage of the library and encourage best practices. With this API, you start out by specifying your data and your privacy unit alongside it. So it's very core that every time you start DP analysis, you start by defining what your privacy unit is, and everything else is built on top of that. Access to the data is always mediated by a compositor. So the recommendations made in the docs is you might load your data up and put it into the context API and then delete your data because the compositor, the context API is not handling all that. And it has a much more concise syntax. It's more data-centric, kind of like pandas. There's a dot notation instead of shifting or the piping in R, and it automatically calibrates the noise scale for a desired privacy level. So no more binary searching. Example of this API is, well, in order to build a context, you specify your data, specify your privacy unit, and privacy loss. And this split evenly over argument is one way that you can tell the context how to distribute your budget amongst the queries. So in this setting, we're saying that the privacy unit is the addition or removal of one contribution, and the privacy loss is an epsilon of 1. So the privacy loss will never exceed 1 epsilon. And we're going to allocate 2 queries. So the way that this API is used is you call .query, and that gives you something that you can chain a bunch of transformations on and ultimately a measurement. And .release is what consumes one of your queries and consumes some of your privacy budget. You'll notice that with this API, it looks somewhat similar to the framework API in the sense that the names are all the same. It's because it just reads from the framework API, constructors from the framework API to like automatically provide this functionality. It's another thing where we want to try and keep the maintenance overhead down. We don't want to be implementing APIs multiple times if you don't have to. So if you have code that works in the framework API, then it also works in the context API, and it'll work automatically in the context API. So I've released 2 queries here, a sum and a count. In the scale parameter you would usually pass into the Laplace is automatically discovered. So just to compare, we have this existing framework API that we've had for years, which we're now calling the framework API. And it implements the OpenDP programming framework. It's constituted of a whole bunch of constructor functions, like make basic composition, make Laplace. These functions return transformations, they return measurements. All that functionality is still available, and it's how we implement new functionality as we go forward. The context API is a new one, and it's just calling the framework API for you in a more convenient way. Nice thing about the robustness of the framework API is that since it always abides by the guarantees that it gives, it helps to keep the code in the context API and other APIs on top of it out of the trusted core. And you'll notice as we go forward, dressing up framework APIs is going to be a very common pattern. You'll see it with the context API, and you'll see it with kind of mimicry of common data analysis tools that data analysts are already familiar using. So 1 year ago, if I were standing here, I'd be saying we need to try to bring the APIs to more consistency with other data science libraries. And now I'm standing here saying we've done that to some extent, and we're going to keep on moving that way. So number 3, all my data sets are in a tabular format. Where are the data frame functions? So we now support making releases with an integration with the Polar's data frame library. It's acting like pandas, but better is kind of the core thinking there. The library, the Polar's library is also implemented in Rust, which is very convenient for us. I'll definitely get into more details on this decision later, but you can do a similar thing with the context API in that now you can pass in a a lazy frame. This is what this pl.scan CSV is doing. It looks like it's loading up your data and from a CSV file, but Polars is not actually doing that. It's starting to build a computational plan. And we love that as differential privacy system makers, because we can look at that plan and determine if that plan satisfies DP. And not only that, we can just read plans that you might write in the Polars API and determine if they satisfy differential privacy. So in this case, you're not learning OpenDP APIs, you're learning APIs for another existing DP, another existing non-DP library. And we can just work with that. Great. So starting off with what one query might look like in the system. So we are selecting, we're computing a DP count of the number of records in the data set. You'll notice that there's some similarity between this and SQL, which is also convenient for us. When you build this query, it's not releasing the data yet. You can ask what the utility of this query is before you make a release. It's saying that we can expect one column in the output data frame with the name of length. The aggregation we're doing on that column is computing the dataset size. The distribution we're using is an integer loss mechanism. We're calibrating the noise scale to 3. And since alpha is equal to 0.05, we can say that with 95% confidence, the DP release differs from the true value by no more than 9.4. So assuming that this is acceptable utility, then we can go ahead and make this release. And we get a little data frame out. So if you keep your eyes on the query up top, the API changes a little bit if you want to do group by. So nice that we finally support aggregate statistics over groups data sets. It's been a long ask. In this case, we're grouping by species. I should mention back here in this original data set, we have pets.csv. This is a data set of say elementary school students and their pets. How many pets do you have? What kind of pet do you have? What grade are you in? So we have quite a few students, 552. When we group by species, it's giving us the same summary table because we're adding the same amount of noise in each of the partitions, and we still get the same privacy guarantee. But you'll notice there is an extra parameter here. It tells you what the threshold is in order to protect the set of potential keys that we release. We only release the keys that have contributions from many different individuals. And the way we determine that is the counts need to be greater than some threshold of 51. So our little data frame is getting a little bit bigger now. We have releases for accounts for cats and dogs, and any other kind of pet didn't have high enough frequencies to make it to the final release. Any questions about this API at this point? Yeah.
Was the threshold chosen automatically, or was that set earlier in the query?
So again?
Was the threshold in that column set automatically, or was that chosen like when you set up the
Yeah, so the threshold, in this case, the threshold was set based on the privacy parameters and the noise distribution. So since the privacy definition was a proxy DP, then it's using Laplace noise. Since we know what the noise scale is, we can determine what the tail bound is and find the threshold parameter that makes it so that the overall query will satisfy a given delta privacy guarantee. So it's just working that things out for you, so you don't have to bother. There are also ways that you can set the threshold manually and figure out the delta for that.
Sit a while.
Hello. Okay, cool. So maybe more technically, not technical, but like non-DP related questions. So first, the context API compositor, does it point in Python, does it point to data in memory? And if so, like you said that you load the context and then you can delete your data, which ideally is what I'd like to do. But does that mean I have to have 2x the data size of memory to start with and then free it up later?
Yeah, so it holds the thing that you pass in memory, so that Python object doesn't go away.
Okay.
I would say that Python is ref counted, so it doesn't necessarily result in multiple instances of the data set in
make an
memory.
internal copy or something.
Yeah, it's the ref count goes up by 1. Yeah.
And then the other thing would be,
Oh, also before moving on, since we set up this in this example, we set up the data set isn't actually loaded yet. It's just pointing to a CSV file. So that isn't hitting memory until you collect.
perfect. Yeah, that's the other thing that I was going to talk about or ask about, which is that at least in either the Polars framework or the REST framework, is it ever possible to get like a race condition on the data if you load the context and then the data is then like wiped from memory because the queue filled up and then we got to dump it? So do you ever get a race condition? Like does the framework handle lifetimes for me, or do I have to specify the lifetimes myself?
Yeah, lifetimes are not something you have to worry about.
Great. I would love not to. I hate them.
So we're definitely not in the business of building compute engines. So we're letting Polars handle that. And I should also mention that like it doesn't have to just be a CSV. It could be a connector for a database or loading from a Parquet file or something else.
Well, but even in the raw Rust framework, because Python at least will try to lock it down for you, but at least Rust may allow you to have race conditions on data. Maybe repeat the question. Oh, did you hear that?
Can you say it again?
Oh, okay. I feel like Python will at least like prevent you from having race conditions most of the time, but the Rust framework would be like, if I told you the lifetimes, it would just do that. So does the Rust framework require me to specify lifetimes? Or like, can you have race conditions in the Rust framework and maybe not the Python framework?
So I'm a little confused where the race conditions would come up in this setting.
Think of like a continual observation setting or a streaming setting. You're bringing in data into a chunk or into some queue. You operate on the data, and then you clear the queue and you put something new in, and you have a fire hose of data coming in. So at some point, you have to dump your data, even if the context hasn't spun up yet. So maybe the context spins up before or after the data is loaded, but before it's deleted or whatever,
Right. So the context is pretty lightweight when it comes to like what it does with your data. In this case, since your data doesn't even exist in memory, it's completely worry-free. The implementation
memory
of the
location can also be cleared at some point, just by some other process, right? So there could be, you have to like lock it, maybe. I don't know. Anyway, this is maybe not the right time to.
Since the Polars library is written in Rust, then they deal with all this kind kind of potential race conditions and batching and streaming data through themselves. Yeah.
What queries are supported with the group by? Do you do like mean, sums, everything?
Yeah, what queries are supported in the group by? So yeah, right now it's counts, sums, bounded DP means. Um, and for the sums, that's bounded and unbounded DP. We also have support for quantiles and by extension medians. We want to add support for variances, standard deviations in bounded and unbounded DP settings. And there's a fair number of other utility related adjustments we'd like to make for that as well. A lot of questions.
Hello, thank you. I'm just curious about how this handles IID versus non-IID data distributions. So here, typically, you set the unit of contribution to 1, but an individual can have multiple pets. And I think that you can handle in the code from what I see. But if you have more complex correlation between users, household, etc., can you handle with this like subtly, or just set a very high level of like, what the unit is and you hope for the best?
So you're asking, how do you handle potential correlation between individuals?
Between individuals, yeah.
I'd say that the privacy guarantees are already tailored towards one individual. So
maybe just to reframe the like correlations between rows. Maybe you define what an individual contribution is, but is it like complex distributions and correlation in the data?
So like in this case, unit of privacy is like one row addition or removal. So we don't need to protect correlations amongst individuals. We're just protecting one individual at a time.
So here typically you're protecting the pet, not the a person who has multiple pets.
Oh, I see what you're saying. Like if an individual contributes multiple rows, then we would update this privacy unit to contributions equals to 7. If they potentially have 7 rows, they're contributing to the data.
But if they can contribute an infinite amount of rows.
Oh, I see. Yeah. So like this is more of a roadmap thing. We'd like to support privacy units specified in terms of the number of identifiers you can contribute to the data set.
Yeah, I guess that's what you were just referring to, is support for user ID as the privacy unit.
Yep.
That's in the roadmap.
Yep, exactly. Cool. All right. Great questions. Thanks for the questions. All right, so getting a little bit deeper, what if we are confident that the set of species is public information? We don't want to protect that. Like, for example, the Census Bureau is releasing counts per zip code, and they don't want to filter away zip codes with in any case. So you might say, if I were to group by species, then do not protect the key set. And this is treated as a more technically as a domain descriptor. We're saying that we're considering only neighboring data sets who have the same key set. We can also say that under grouping, when grouping by species, we know that the max partition length is 1000. So there's never any case where the number of records corresponding to an individual species will be greater than 1000. This is convenient for us because it lets us calibrate um, privacy guarantees according to and account for kind of difficulties around floating point arithmetic and can make us um, can allow us to check to make sure that there's no data overflows or other conditions like that. So we're protecting against those kinds of potential vulnerabilities. So this is you might be you're definitely already familiar with like bounded DP and unbounded DP. We're saying this is a setting where you're kind of like an upper bounded DP. We know data sets are no bigger than 1,000. So given this piece of information, we can build up a more complicated query. So we're going to do a group by on species again, but this time we'll submit 2 queries simultaneously. One's going to be our DP length, and one's going to be our DP sum on the number of pets you have. The library will automatically distribute the budget amongst these 2 queries. We have a question from Ashwin.
Previous slide. If I understand this correctly.
Nice.
Hello. Yeah, if I understand this correctly, what you're saying is you now have differential privacy conditioned on some exact invariants that are exact statistics. The privacy semantics of differential privacy combined with invariants is very complicated, and it's not even clear what properties it may satisfy in terms of composition and activity and all that. So what does this do? Like once you do this, like, do you know what privacy you're ensuring in your program? Can you talk a little bit about that?
Yeah, so this is one restriction on the set of possible input data sets. The data sets, we're only considering potential data sets that may vary by the same underlying key set. So I don't know if it still composes under DP in the same way, because we're limiting the set of potential input data sets.
Yeah, it's a lot more complicated than that. It's a longer conversation. We should have that at some point of time. But invariants are notoriously hard, and they blow up the privacy semantics. So we talk about it offline.
Yeah, so I agree, and this is part of the warnings on the documentation around this kind of functionality. It was kind of necessary for a use case, and it can kind of simplify deployments in cases where key sets are not protected. Okay, so given this query, I can also summarize what the utilities of the queries will be. Of the statistics will be. We'll expect 2 columns in the output. One column is named length, computing the sum, computing the counts. And the second column is the sum over pets. It tells us what the noise scale parameters are, and information you would need to construct confidence intervals around the DP releases that are made. And when we make this release, we find that there is indeed one individual, one student who owns a pet alligator. So watch out. All right, so why polars? It gets us out of the business of building our own compute engine, which is a nice start. The API gives us these flexible SQL-like expressions. The lazy compute model is kind of like a core value proposition for the polars library, but it also dovetails well with what we want in DP, in that we want statically analyzable compute plans that we can analyze and determine if they're satisfying privacy. The internal representation of the compute being done in polars is with Apache Arrow. So this allows easy interop with other systems. There's a new PyCapsule API for Arrow, where you can take as input many other data sources from different databases, software tools, and various languages as input for the computations that you want to run in polars. All right, so those are all things that we had promised last year. Some more things have happened since then as well. We've expanded our functionality around plugins. So you can plug in your own Python code to implement custom mechanisms and transformations. The way this works is you supply 2 Python functions, an algorithm implementation, and a privacy or stability map. It tells you how much the outputs can change, when the inputs change by at most a bounded amount. And they behave just like OpenDP built-ins. You can chain them, you can compose them, you can mix things that are written in Rust with things that are written in Python. So everything works with the privacy calculus. And this is really great for experimenting, prototyping new contributions to OpenDP. I think it helps lower the bar of entry for people who want to make contributions to the library. We're not asking you to go out and learn Rust unless you're interested in learning Rust. You can implement them in Python, and we can move them into Rust if that would be helpful. We also lets us incorporate algorithms from other DP libraries. I've used them extensively when writing my book, Hands-on DP, in order to demonstrate how differentially private mechanisms are implemented and work. We now also support building your own domains, metrics, and privacy measures from Python as well. They also behave just like OpenDP built-ins. You can chain compose them. It's great for experimentation. So a quick example, we're going to make, on this low-level API, we're going to make a transformation constructor. This transformation is going to take a data set that's a 2-dimensional NumPy array, where our rows are contributions from different individuals. We have some domain descriptors on this. We're saying that this transformation accepts and reasons about, makes promises about only 2-dimensional NumPy arrays that have 2 columns and have data type of float. On this transformation we're building, we're also saying that neighboring datasets differ by additions and removals. And the function we're going to compute is just going to compute a d-dimensional histogram over the data. You specify the number of bins, specify some bounds. It'll rabble it out into a big vector of counts in each bin, and output into a vector. So this is characterizing how far apart datasets can change and what datasets can be and what the computation is going to be run on it. And how do we reason about how far apart datasets are on the output? Great. So at a high level, this whole thing is saying that when you compute a d-dimensional histogram over this two-dimensional array, then visits can differ in terms of an L1 distance, and we have a stability map that doesn't increase the distance or decrease the distance between output data sets. And the way you might call it is pass and bounds for each dimension of your data. The specify the number of bins that you want to run. You get a transformation for a d-dimensional histogram. If I know that adding or removing, or if I know that I can add or remove at most one row from the input data, then the sensitivity, the L1 sensitivity of the resulting vector is 1, based on the promises made by the stability map. And then the computation can be obviously run. So this is, again, this is very low level implementation details. If you were to go and implement things yourself like this, because you want to make an extension, you can register them with the library and they'll show up in the context API. Another example of an algorithm you might want to implement with this is like above threshold. Like this is how it would look or could look. So this is a function. It's taking the threshold and a noise scale. It's going to, the way this works is it's going to take a stream of data and it's going to return true the first time a value in the stream is above the threshold. Approximately. The function here is starting off by computing a noisy threshold. Its noise is a threshold. And building a queryable. A queryable is something that we had talked about last year, and that it's kind of like a state machine, and that you can store some state inside of it and repeatedly query it with well, queries that depend on the implementation of your function. So in this case, we're using the queryable to model a stream, and we're saying that each time you get a new entry in your stream, we'll noise it, check if it's above the noisy threshold. If the value is above the noisy threshold, then we're going to return true and terminate this queryable. So I bring this up because it kind of shows a couple neat aspects of this plugin system, and that you can define your own queryables from Python. You can also define your own domains from Python. So I'm saying once I actually make this measurement, I'm saying the input domain is all streams where values in the stream are floats. I have a way of saying that the sensitivity of the stream is bounded, and this code here below shows that an example of how you might build your own custom domain by specifying an identifier for the domain and specifying a function that checks if a value is a member of the domain. You can also kind of tag along extra information about the data that is in the domain that can be useful when you want to build up other higher level computations. But I think this is a like really fantastic learning tool if you're kind of building. If you're teaching a TP class, for example, you can say, well, here's an API, a structured API that normalizes access and that requires all the pieces of the of your guarantee, your stability, your privacy guarantee to be specified. So if I were to call this, I first make an instance of this measurement by specifying the threshold and noise scale. I give it a stream. This is a stable stream. I get back out a private stream. This private stream I can query multiple times until ultimately it will reject my queries because it's terminated the queryable because I've gotten a true. So I just queried it multiple times with a 2 is much less than a threshold, so it's probably going to emit false. A 3 is probably also going to emit false. Once I pass it 6, then it emits, the queryable emits true for the first time and terminates itself, and then any call after that, it's going to fail, as we expect. So PCA is kind of an example of an API that we implemented that is built on top of these plugins. It was convenient to make use of like NumPy for the implementation of this algorithm. This is another example of a case where we take the APIs that we built in terms of the framework, and we dress them up to look like APIs that data analysts are more familiar with. Lots of work on documentation. We have 4 tracks. Getting started is covering these high-level APIs like the context API, like usage with pollers, like scikit-learn. We have more granular API docs. We have theory docs on how the fundamentals of DP are applied in OpenDP, and then finally how to get involved with a project. So previews of upcoming attractions. We want to remove this pesky line from your code, dp.enable features. We want to have much better coverage of the in the library for what things have been proven and vetted. Another thing is odometers and filters. So going back to the context API, with filters, we can drop this last row, privacy evenly over 2. You can specify those privacy losses as you go. With odometers, you can also drop this privacy loss upper bound to get the most essential representation of just data and privacy unit. A lot more pollers functionality, more statistics, more data set pre-processing transformations, working with user identifiers, as has been brought up in the comments. And it just goes on and on. So I left a link on the bottom, prioritization poll. Would love to have your thoughts and opinions on what would be useful. If you have use cases, what things would be best served by the functionality in the library. There's definitely more here that we can implement in pollers than our development capacity can handle in the next year. So it's good to know what would be useful. For the roadmap, all the above plus potentially more R package functionality, bringing the context API over to R. Pollers has APIs for R. We could bind to them as well. Plugins for R as well. More algorithmic primitives. There's low-level mechanisms that you can use to build up and integrate with your software systems, or pull off and use in your papers. Privately estimating clipping bounds is just like a usability thing. It can be difficult for people to estimate their hyperparameters. So if we can help with that, that'd be great. more work on numerical and analytic compositors, potentially local DP mechanisms. That's been had some really great contributions that help move that along. And also like functionality for generating synthetic data with utility guarantees. Similar thing there. We've gotten great contributions. We can keep on shepherding those along. And you can influence the roadmap. So we have this poll. Please fill the poll out, and we'll talk about it tomorrow to help discuss what things are most useful. Wrapping up, you can get OpenDP from the Python package on PyPy. It's also available on R. It's also available on crates.io, which is what the package distribution system is for Rust. All our source code is open source. It's open source and open contribution, Apache MIT licensed. So don't hesitate to join. Documentation is available at docs.opendp.org. We have great resources there. And join the Slack and send me a message if you have questions. Great.
So we're going to be